This is going to be a presentation about Flames and about the things that we're doing with Flames. Here's the outline of the presentation that I'm going to give this morning, and in particular, some of the future enhancements that we have going for Flames. You know, it's been a blessing for me in my career to have worked on this product. And it's just amazing to me that even after having worked on it for so long, that I'm still just so excited about the stuff that we're doing and the new features that we're adding. So I'm going to get a chance to share my excitement with you this morning and tell you about some of the things that we're doing at Ternion. And we have been in business for a long time. We celebrated our 30th anniversary this year. So it's been a tremendous experience, and we have some customers that have, lots of customers that have contributed to our success. The last few years at Ternion have been some of the best years that we've had in terms of revenue and profits and also new features and new capabilities and new business. So we're very excited, and as I've mentioned already, we're doing the things that we need to do at Ternion to make sure that we continue to support our customer base for many years to come. So just a couple of slides about the history of Ternion. As I already mentioned, we've been in business for 40 years. We started in April of 1989. We started the company specifically to build this software product line that we now refer to as Flame. So this is exactly why we started the company. We had a passion for creating a product that would make a big difference in the simulation marketplace. I'm going to tell you a little bit more about that in a minute, and I'm very thankful that we've been able to pull it off, that Flames has turned out to be just what we envisioned it to be, and that we keep coming up with new ideas to make it better. So that was the focus of our business right from the very beginning, to build this commercial software product called Flames. But we also build custom simulations based on Flames. And so we have a services department, and that's the side of the company that Joel manages. So we build custom simulations for people using Flames. So those would be not part of our product line. They're applications built on top of our product line. So those are the two parts of the business. The side of the business focused on building the product line, and the side of the business that uses the product to build custom simulations for other people. Our customers are people all over the world. All of the services here in the U.S. have used us and are using us. Governments all over the world. We spent a lot of time the last 3 years in Taiwan, and we built a wargaming system for the Air Force. They practice defending themselves against attacks from mainland China in a building built specifically to house our simulation. It's a really big program for them. And we built the first one for them over 10 years ago, and they came back to us and said, we have a whole bunch of new features we want added. So we just built, it's called the Distributed Wargaming System Enhanced. But we do a lot of work in Europe and a lot of other places, and then of course a lot of other companies, commercial companies, government contracting organizations use our products. So enough of the background on Ternion. Let me tell you a little bit about Flames. Flames is very different, we believe, from anything else that you're going to find here in Orlando this year. And in fact, in our own humble and unbiased opinion, it's different from anything that you're going to find anywhere in the world. And we have customers in this room and around the world that will back that up, that they've not been able to find anything that's quite like Flames. The military simulation world tends to divide their simulations up into 3 categories. The first is what they call live simulation. And live simulation is real people using real equipment, real guns, real airplanes, real tanks, but they're using it for purposes other than war. So they're not involved in a battle. They're using it for training, for testing, for system development, whatever it might be. That's considered to be live simulation. And the systems that they're using are called in our domain called live systems. Now, the second type of simulation is virtual simulation. That's the same real people, but using fake equipment. So they're using a cockpit flight simulator that's made to look like a real airplane. They're using a laser gun or a tank simulator. So the hardware that they're using is fake, is simulated, but the people are still the same, and they're trying to use that hardware in a way that's very similar to the way that they would be using the real systems. And then there's constructive simulation. Constructive simulation, there are no real humans or real equipment. It's all simulated on the computer. And so that's the LVC. If you heard that acronym, you see it out there on the show floor all over the place, LVC, live, virtual, constructive. And it's true that these three types of simulation frequently work together. Live and virtual and constructive, and a lot of times it's the constructive simulation that's providing the virtual environment or the synthetic environment for the live systems and the virtual systems. Flames is a framework for developing custom constructive simulations. So it's not what you would use to develop a virtual simulator or to develop, of course, live systems. But it does frequently get used in context with live systems and with virtual systems. So we do that all the time. In fact, there's a lot of talks that you'll hear at the show, people talking about the challenges of LVC simulation. And we wish that people would get a chance to come see what we do for our customers, because hooking up LVC stuff is just like a cakewalk for us. We just do that all the time. We're talking to other things all the time. We have a lot of experience doing it. It is a very challenging thing to do, but Flames is built specifically with features that make it really easy for us to connect our constructive simulations to these other systems. So again, we're a framework for constructive simulation. And our particular market, if you want to look at the market now from another standpoint, look at it like any other software market out there, our particular market is unique. Well, it's not unique, but it's very different from most other software markets. And the reason is primarily because the simulations that we need to use, constructive simulations, are very diverse. There's not one set of requirements that are the same for the whole marketplace. It's not like an accounting package where most companies all have similar things that they need to do for their accounting and bookkeeping functions. So you can write a particular program that will work for lots and lots of companies, thousands, millions of companies even. Our market, everybody has a different set of requirements. And I bet if we went around the room and talked to everybody in here, every one of you would describe your requirements. And unless you work together in the same office, you probably don't have the same requirements as the people sitting next to you, or the people across the room. And so the constructive simulation that you might need to meet your requirements wouldn't work for the person that's somebody else in this room. So we might have 20, 30 different constructive simulations that would be necessary. Because we have Army, we have Air Force, we have Navy, we have Marine Corps, we have Coast Guard, we have training, we have testing, we have mission rehearsal. There's all different kinds of requirements. So very different software market. What that means is that we need many different simulations. And there's not going to be a single simulation that anybody's ever going to be able to build that's going to be able to take over a very large share of the market. It's just not possible. There are thousands of different constructive simulations, literally, and many of them have only half a dozen users because they have a specific thing that they need to simulate, and these are the only people who know how to do it, and they're using that simulation just for that, and nobody else in the world would find any value in that particular simulation. So that's the challenge that we face, and so it'll probably never happen that you'll be able to get on the internet like you can. Say you need a photo editing package. Well, what are you going to do? The first thing you're going to do, you're going to get on Google, and you're going to say photo editor. You're going to say, give me the best photo editing packages. And somebody's going to come up, they're going to give you a top 10 in 2019, and you're going to download some trial copies, and you're going to see if it's going to meet your needs. You'll find the one you want, you click it, and you're going to download it. We'll never be able to do that for constructive simulation, because there's never going to be simulations out there that are going to meet the unique requirements that we have in the marketplace. The other problem that we have is our requirements are constantly changing. Accounting's kind of the same, except for what Congress does to change the rules every now and then, every couple of months. The accounting still pretty much the same. Photo editing is pretty much the same. In our world, everything's changing. The threats are changing. The systems are changing. Everything's changing. So our simulations have to be constantly updated. So even if you did find a simulation off the shelf that meets your requirements, it might be only a year and your requirements are changed, and now the simulation isn't going to work for you anymore. So we constantly have to update our simulations. And this is the challenge. So when we started out developing a product that we hoped to sell and be able to feed our families with for a long time, we knew that we would never be able to just build this point design and be able to sell it to lots of people. We knew that this was our market, and we had to come up with a product that would be useful in this market. So these are the challenges that our particular market faces that we try to address with our product line. The first one, of course, is that simulations are really expensive. Generally speaking, if you know anything about software development, the life cycle cost of a software system is directly proportionate to the number of lines of code in the system. And constructive simulation have lots of lines of code, so constructive simulations are really expensive. And you may be associated with an existing program. The worst one that I ever heard of, most expensive one, was a program called JSIMS. Some of you maybe heard of JSIMS. They spent $850 million on JSIMS. $850 million. And they worked on it for 10 years and then they canceled it because they didn't understand right from the very beginning that you can't build a big complex software system like that from scratch. And that's what they were trying to do, and there's a lot of us in the industry said, you're never going to make it. And after $850 million, they figured out, nope, you're right, we can't do this. So they're real expensive, but it's not uncommon for support contracts for larger constructive simulations to be 10, 20, 30, 50 million dollars a year just to maintain the existing simulations that we have. They're incredibly expensive. The other issue is, this at least in the U.S., I can't speak for other countries, but in the U.S., one of the problems that we have is that we still try to develop constructive simulations like an old technique. It's called the waterfall approach. We'll write an RFP, we'll send it out, say somebody build us a simulation. It's a new simulation. There isn't one out there that's exactly like what they need, so they've got to get something. And so somebody stands up and says, I've built these things before, I'll build them for you, give me 2 years and I'll deliver it. Well, most of the requirements state what kind of systems they want to be able to simulate. And that's what they're focused on. And so all the energy is put into writing the sensor models, the tank models, the command and control models, and putting all that together. In 2 years, you just don't have time. It doesn't matter who you are. You don't have time if you're starting from scratch to build a mature, robust simulation architecture. You don't have time to build a really nice polished user interface, especially when the requirements and the money that you get aren't paying you to do that. They're paying you to build some kind of functionality to meet the modeling requirements of the organization that you have. And so ultimately, the architectures that we see in the constructive simulations, they're what I would consider to be extremely immature. They weren't designed to be expanded and enhanced and easily have things plug in. All the energy, again, went into models, and they're all just strapped together with bubble gum and rubber bands. You look under the hood and you see spaghetti code, no matter what language, what it's written in. So with our requirements constantly changing, we have to update these simulations that aren't designed really to be updated. I gave a briefing one time to the program manager. He was the program manager worked for the contractor that had the contract for one of the big U.S. government constructive simulations. And if I gave the name of it, some of you will have heard of it. I'm not going to give the name. And I was talking about how Flames was easy to modify. And he, at the end of the presentation, he said, we're modular too. We can be modified. Not a problem at all. I don't see anything special. What's different about your product versus what we do here at the simulation? I said, well, sir, let me give you a little questions. Suppose this happened, and you tell me what happened. You take your simulation and you give it to a team of people out on the West Coast, and you give them a set of requirements how they want to change the simulation. So you say it's really easy to modify. Give them requirements how they want to change it. They're out on the West Coast. Take another team, give them your same software, put them down in Florida. Let them make changes to your simulation and give them a different set of requirements. And give them 6 months to make the enhancements. And during that 6 months, don't let these two teams talk to each other. Just let each of those two teams go and make the changes that they need to make to enhance the simulation to those two different sets of requirements. After the 6 months, take the software that they've modified, give it to a third team, not the same team as the first two, give it to a third team and ask them to integrate the changes that each of those two teams made into a single simulation. And don't let that team talk to the other two original teams. Just give them those two sets of modified software, bring them back together and let them change it. I said, how hard would that be for that third team? He said, oh, that would be impossible. I I said, there you go. I said, if that was Flames, that third team would have that software integrated in less than 48 hours without talking to the other two teams. Because of the maturity of the interfaces and the way that things plug in, everything's plug and play. You take the plugins from that guy, the plugins from that guy, and probably be working by the end of the day. And you'll find out in this room how that happens. Let me ask you a question. When you need to add a new graphics card to your computer, and you're not an electronics guy, how long does that take? Why? You get on the internet, you search for the graphics card, you click on the thing, in 2 days, Amazon ships it to you at Amazon Prime. You get the little 3-step card, you turn off the power, you open it up, you plug it in, you close the box up, boom, you have faster graphics on your computer. That's how new functionality is integrated into modern hardware systems. That's how new functionality is integrated into Flames. You just plug something in and it shows up and it works. So you're going to hear more about that later. That's not what we have with most U.S. government constructive simulations. Multiply all this high cost by the fact that we've got hundreds and thousands of different constructive simulations that are all facing these exact same problems, all need to be upgraded, all need to be changed. And we have an incredible amount of money that we spend developing simulations and maintaining simulations. The biggest cost, I think, though, is that because simulations cost so much and it takes us so long to get something built and so long to make changes to that, most people don't have the simulations that they need. I will give a briefing sometimes to people, and I'll open up the briefing, and I could ask you guys the same question. We don't have time to do that this morning, but I'll go to the leaders of the group, and I'll say, let me ask you something. If you could wave a magic wand, and you could create the simulation that would do anything that you wanted to do, tell me what it would look like. So they can do it right away. They don't have any hesitation. Well, we need something. This, we want this, and they go down the line and let them say what they say. And that's okay. Let me ask you a question now. What percentage of that do you have here today? What percentage of that do you have available to you and working right now? And sometimes I get the answer. They just look at me and say, well, none of it. I don't have anything that can do any of that. You go around, I bet you, I don't know if this is true, but there's probably people in this room that don't have the simulation that you would like to have. That might be the reason you're in Orlando this week, because you don't have the simulation capability that you want. That's wrong. And how much is that really costing us? You can measure the cost of that sometimes in human lives, because we don't have the tools that we need to build our systems, to train our warfighters, because simulations cost too much to build and they take too long to build. The other issue is that simulations that we have are generally really poor quality. And what I mean by that is that, for one thing, they're difficult to use. I know of an old simulation that's used in Huntsville, and I can't verify this. I just had somebody tell me this. They said that in the entire history of the simulation, there's only been 2 scenarios built for it. And they just used those scenarios over and over and over again with minor tweaks. And the reason is that both of those scenarios each took 100 man-years to build. It's because that's how incredibly hard that simulation is to use. That just seems impossible to me, but the person I talked to who used it and said, yep, that's really true. But even if it's not 100 man-years, even if it's a half a man-year to build a scenario, even if it's a couple of weeks to build a scenario, sometimes we don't have a couple of weeks. They don't function correctly. They don't work like they're supposed to. They crash a lot. They don't have good documentation. Some of you guys who have your simulations, how many of them are really well documented? You can pull it if you have a question or problem. You can just pull the documentation and find it. We don't have enough time in these rushed, expensive development efforts to write good documentation. People don't spend enough time doing that. They don't have all the features that people need. People say, oh, it doesn't do this. The people are constantly doing workarounds to try to get things to work the way they need it to work. And they're not polished. If you bought an off-the-shelf product and installed it on your computer and used it and it worked as poorly as some of our constructive simulations, you'd send it back. In that 30-day trial period, you'd say, forget this, I'm not going to use this thing. But we don't have a choice with our constructive simulations. They don't have the polish that we have come to expect with software in other markets. And it's because of the market that we face. So, Why did we build Flames? What was our idea when we started this company? Why did we think we could make a difference? Well, you kind of figure out from this, there's two reasons why we started. We started the company as a whole and what we're trying to do. The first is cut that cost down, cut it way down. And if you compare the cost of existing constructive simulations that are based on Flames and compare that to the cost of other constructive simulations, we're usually at least 10 times cheaper. At least 10 times cheaper. In the case of JSIMs, no doubt we would have been 100 times cheaper. It's just crazy how much money gets spent and how a different way of building things can change the game completely. The second thing we're trying to do while making the simulations cheaper is just make them better quality. We want the quality of our constructive simulations to be on par with the software that we use in every other market. So that's the focus. Better, faster, cheaper. So here's how we do it. First, just the top level. So what is Flames? Flames is not like what you see in other companies. It's just a very different kind of product. The first thing to understand is that Flames is not a simulation. Flames can't simulate anything. Nothing. Can't simulate a tank, can't simulate an airplane, can't simulate a command and control decision. It has no modeling capability in it whatsoever. However, Flames has been the foundation for over 100 different simulations. And that's the difference, is that Flames gets used to build constructive simulations, but it is not itself a constructive simulation. What we call a Flames-based simulation, what we call simulations that are based on Flames, we call them Flames-based simulations. And a lot of people will come up and say, I use Flames. Well, nobody just uses Flames by itself. They always use Flames with something plugged into it. And so a lot of our customers call their simulations by a different name. And it's appropriate that they do, because it's not just Flames. It's based on Flames, but it's a different simulation that's been built on top of Flames. All of these simulations, though, even though they're all very different, they serve different markets, they're in different countries, they serve different services, different systems, they all use 100% exactly the same framework. So here's how we do it. In a simulation, one of the ways to group the software together is into what we call infrastructure software and modeling software. Modeling software is all the software in the system that is intended to simulate real-world systems. So it's a software that simulates tanks and airplanes and missiles and ships and submarines and command and control and communication devices and jammers and all the real-world stuff, the natural environment, the man-made environment. That's all, and that's the stuff that we typically think about when we think about a simulation, and that's the meat. But because it's a computer simulation, every simulation also has stuff in it that we refer to as infrastructure software. It's the stuff that doesn't simulate stuff in the real world. There is no real world analog to it. It's the memory management software. It's the graphical user interface. It's the map software. It's the inter-process communication software. It's the timing software. It's the object instantiation. It's the software database software. All that stuff that's there just because it's a computer simulation. Well, it was our contention that we could make a very clean line between the infrastructure software and the modeling software. And that's what we strove to do. So Flames is all infrastructure. It has no modeling capability whatsoever. What we looked at, we said, look at all these different simulations out there. They all have to have some kind of a graphical user interface to enter the data. They all have to have some way of storing that data on the disk. They have to have some way of managing memory. They all have all this stuff that's all common. Even though it's common, everybody builds it from scratch over and over again, and there's no compatibility. We don't have common database formats. We still don't have common terrain formats. We can't share after-action review stuff. You can't take code from one simulation and plug it into another simulation because it's all, the infrastructure software is all completely different. There's really no reason for that. You don't need to have different infrastructure software. The modeling software has to be completely different. It has to be that way, but the infrastructure doesn't. So Flames contains no modeling software whatsoever, and it contains all the infrastructure that any constructive simulation would ever need. It also contains this interface to the infrastructure software that I think is where the real magic is. Why is it when you buy a computer and you want to upgrade the graphics card that you can get on the internet and order a graphics card and plug it in? It's because somebody figured out how to divide the motherboard functionality from the peripheral functionality. Somebody figured that out. This is where we're going to draw the line. There's going to be these things that are plugged in on the outside, and there's going to be this stuff that resides on the motherboard. So somebody figured that out. And then somebody also figured out how to put those slots on the motherboard. And those slots are the magic. So now vendors can all build to those slots, and if they conform to the standards of the slots, you just plug stuff in. And somebody figured that out, and because they figured that out, computers are no longer big monolithic systems. The first computer that I worked on was a CDC, Computer Data Corporation thing that I programmed with punch cards. That's really how old I am. And it had 128K of memory, not meg, K. And that memory unit was the size of 2 refrigerators, and it was cooled by water. So when the memory had a memory problem, you had to call the plumber. It was crazy how things were. But why we don't have that anymore? Because computers aren't built by single vendors anymore. They're built. The big guys are like Dell and HP. They're integrators. They don't build most of the stuff. Third-party vendors all do it. They build to standards, and they all plug this stuff in. It's component-based architecture. And that's why computers get cheaper and cheaper all the time, why Moore's Law applies to electronics industry. You get better and better capability all the time for lower and lower cost. The hardware guys have figured this out. A lot of guys in the commercial software world have figured this out. In the military constructive simulation world, we haven't figured it out. Well, Ternion has figured it out. We know how to build a motherboard and how to define slots so you can plug stuff in. And that has changed the game completely, just like it changed the game in the hardware world. We didn't invent this approach to building systems. We just looked around and saw other people who were being successful and said, what can we learn from these other smart people out there about how to build software systems? So the models are implemented as plugins that plug into the system. And so when you want a different simulation, you just create different plugins, and the infrastructure stays the same. It's exactly the same. And so we built all of our simulations based on that same infrastructure. So typical simulations would look like this. They're all unique code, they all have a unique user interface, unique database stuff, unique memory management, it's all unique, all the models are all unique. You can't share a single line of code. People talk about software reuse and sharing stuff. That's a joke. It doesn't happen because the architecture, there is no motherboard. Nobody's divided this stuff up into motherboard versus slots and how to define nice, well-defined interfaces to make it all plug together. Flame simulations look like this. The majority of the software is Flames. And we have that interface well-defined, and we just plug different things into it. And we've got these simulations all over the world that are built for different people, for different organizations, for different purposes. War games, hardware in the loop, training, live virtual constructive stuff, everywhere. They all use exactly the same framework. So what effect does this have? Well, just like in the hardware world, first thing that happens is cost goes way down. And here's the reasons why cost goes down. First of all, if you get rid of a bunch of unique code and every one of your simulations can share the same code, that's just code you don't have to write. So when somebody contracts with Ternion to build a custom simulation, we got 80% of the code already written. It's already tested, it's already in use, it's mature, it's documented, it's polished. We start day one with all that code already written. We know how it works, it's all set up. We have all the interfaces all completely defined. So we're not sitting around scratching our head trying to figure out what's the class hierarchy supposed to be and how we're supposed to do this and how we're supposed to do that. We know how to do all those things. We have the spec for what a plugin looks like. Everybody at Ternion has built dozens of things that conform to that spec already. We'll go to a customer, have a kickoff meeting, and find out, it's not the kickoff meeting, but we sit down and start the project, and he tells us what he wants. We come back, and by the end of the day, we have people writing software. Because we already know exactly what the architecture is. We already know what plugins look like. We need a sensor model that looks like this. We know what every one of our sensor models looks like. We need a command and control model. We decompose the system immediately into the proper classes, and people start writing code immediately. And sometimes we deliver initial operating capability in a month. We show it to the customer and say, is this what you think? Is this what you had in mind? The scenario development tools all work. The 3D display works. Everything works. And we looks at his models and says, yeah, that looks really good. And then we keep going. The second thing is, because we have this well-defined interface for how we write plugins, the effort required to build those custom pieces is dramatically reduced. And we know right when we start that the interfaces that we've defined are going to work because we've been using them for almost 30 years. We know that they work, so there's no risk. We're not going to have design reviews and trials. We don't have to do any of that stuff. The design's finished. We're just building individual classes. We got to work on design of those things. We got to test the individual classes, but the architecture is mature, polished, reliable. We just plug stuff into it. Just like when you build a graphics. When the guy that builds a graphics card, a graphics card vendor, he's not testing the motherboard. He doesn't worry about the interfaces on the motherboard. He doesn't have to pay any attention to that. That's done and it works. He just works on building his own card and gets his card working, and then he knows once it works, it's going to plug in and it's going to work just fine. That's how we build models for Flames. So the effort of the custom software development is also dramatically reduced. The other thing that's really significant is the integration step. Just like it just takes just a few minutes to plug that graphics card into your computer, that's, again, how simple it is to plug stuff into Flames. And I'm going to tell you more about that later in this presentation. The key thing about this, or an example of this, when we were doing constructive simulations before we started Ternion, when we built a new capability, we would spend half the time developing that new capability, and the other half of the time we'd spend modifying the existing software to be able to recognize that new capability. And that happened every time we had to modify. We're constantly tweaking the architecture. It's like the way the old monolithic computers were. If you wanted to add new capability, new memory to a computer, you better know how to use a soldering iron many years ago. In fact, you might remember this. The Macintosh came out. What was the name of the first Macintosh? Anybody remember? It's called the Mac 128. Because Steve Jobs said publicly, nobody's ever going to need more than 128K of memory in a computer. He was a brilliant guy, but he kind of missed the mark there a little bit on that one. So they realized real quickly 128K of memory wasn't enough, so they came out with a new computer, Mac 512. That was the second Macintosh. Could you just plug stuff into the Mac 128 and make it a Mac 512? Nope. Then buy another computer because they didn't have this interface stuff figured out back then. Of course, that's all changed today. And that's the same thing. We're still having to rebuild things internally in order to expand things. The other thing is the quality. You have to just think about this. Even a bunch of guys in North Alabama, if they're given this kind of opportunity, they can build something really special. We're definitely not the smartest guys in the world, but getting out of the government-funded software development effort and spending our own money to build this thing gave us the ability to build software like other commercial software companies do. And Ternion's been in business now for over 30 years. We've had 30 years worth of users contributing to our products. Not just one program office telling us to do what they need to do. We've got people all over the world that are using it. So that means we have more requirements that we've had to satisfy, more use cases than a typical constructive simulation, more testing, more feedback, and that's been going on for 30 years. Give any group of people the opportunity to work in that environment, they're going to be able to build something that's really polished, really mature, that's going to be really high quality. If they get a chance to work on it for 30 years serving customers all over the world, those customers are all renewing their software licenses, they're all paying to keep Flames being updated. It just gives you an environment where you have a chance to succeed at doing this. We also have, because of 30 years, we have an unparalleled feature set. And I don't like hyperbole, so I don't put a lot of that in just statements like this, but that statement is true. Compare the features that Flames-based simulations have to any other simulation. Bring it in, throw me in the ring, let me duke it out with them. Nobody has the feature set that we have with Flames. Things that we can do with our constructive simulations, some people don't even realize that's even possible. And some of that you're going to actually hear about in this presentation later on. And then, of course, polish. A lot of what we do every version, in fact, version 18 was a lot of polish. We're just adding new little features and stuff. Typical government simulation programs just don't give those software developers the time and the money to sit around polishing it all the time. Those guys are smart guys too, guys and gals. They could all do this too if they had an environment where they're allowed to do it, but they don't. they're always, what's the next sensor model we have to write? What's the next missile model? We got to be able to do this. Got to be to really sit down and polish it and adjust it and tweak it. There's no money to do that kind of stuff because there's so much money spent on just getting the basic functionality. There's two ways that you can use Flames. Flames was built for software developers. It's built. We knew that this was a framework that we're going to be using to build custom simulations. So it's been built to actually allow people other than Ternion to use it. That was our target audience. And we figure if we can build it so other people can use it, then we can use it too. If it's that good, it's that well documented, that interfaces are that polished so that we can sell it to somebody else and they can build their own constructive simulation, well, then it's going to be good enough for us to be able to use as well. So that's been our target. So that's one of the ways you can use it. You can buy the development suite and you can build it. You can build a simulation yourself, or you can let Ternion build it. If you buy the development suite, you've got all the tools you need to be able to build your own constructive simulations. Our foreign countries usually do this, not all the time, but they usually don't want a U.S. government contractor build their constructive simulations. So they buy it and have their own software developers do their software development. And there's a lot of people who have built really nice simulations. Sometimes we don't even know who they are. We meet them at a trade show like this, we sell to them, they can't tell us what they're doing, and they're off selling Flames-based simulations to their customers. The other one is to let us do it, and a lot of companies don't have, or organizations don't have a software development team, and so they choose us, and obviously we know our software really well, we're really efficient at it, and we can usually develop it more cheaply than other people could do it, if they're able to let us do it for them. So we have a lot of custom simulations that we build for other people based on Flames. Well, switch gears now. Talk a little bit about version 18. Our development cycle is now synced up with ITSEC. We tried a few years to release new versions more than once a year, and our customers saying, no, that's too fast. And if it was longer than a year, we couldn't get the new features to them soon enough. So we pretty much decided over the years on the annual major release cycle, one major release a year. And we do that right before ITSEC. So a lot of times we're doing our final testing while we're eating turkey on Thursday. One of the biggest things that we did in this version is we took, and this won't make any sense to people who aren't Flames users, but for those who are, all of Flames data is stored in a scenario database, and I'm about to actually tell you more about that in a few minutes. But the database did not have the scenario file in it. And in this version, we moved the scenario file into the database. And so there's a lot of reasons why we did that. And they're listed here on this chart. But one of the things it lets us do is have a really nice scenario browser. So when you click on a scenario, you're not going through the normal Windows or Linux file browser, and you click on a scenario, you get a nice description of it. It's really nice for new users to Flames to kind of click around and pick a scenario. And this lays the foundation for some new features that we're adding to the product. We also added a bunch of polish. And there's a whole bunch of things on here. I'm not going to take the time to describe them, but again, we focus on the product side of the company doing just infrastructure stuff. The product side of the company doesn't do any modeling. We do that for custom customers, for custom simulations, but again, the product doesn't have any modeling in it. So we spend all of our money every year polishing the product, adding more features to the capabilities. That's why I can say without any doubt that we have a set of features that nobody else in the world has, because we spend all of our R&D money every year adding new features and new polish to the product. So I'm going to tell you now some of the things that we're working on, and this is new stuff. I'm going to use this as an opportunity to also tell you a little bit about how Flames really works. So I've been talking about what it does and how we can plug stuff into it, and you're going to learn a little bit more about just how it is that we accomplish that underneath the hood. And we have two major initiatives that are going on right now. There's a whole bunch of other things that are going on, but these are two of the biggest ones that we have. We've actually started working on these. They just are going to take us more than one release to get finished. So some of version 18 and some of version 17 is actually working toward getting us to this point. One of these things we're actually hoping will be out in version 19. We're targeting that. And the other one won't make it in version 19 next year, but hopefully soon thereafter if it turns out that it's going to work. A little bit about internally now. We're going to dig down a little bit more deeply, but hopefully in a way that you don't have to be a software developer to understand it. This is a really high-level picture of the internal architecture of a constructor simulation. You've got the modeling software, and when a model software needs to do something, and this is not a Flames-based simulation, this is a typical constructor, and really typical software in general. If they want to write something to the disk into a file, they call it operating system call to open the file up, and then they make write calls, and they save the information in the file. If they want to allocate some memory, they call an operating system routine to allocate some memory. If they want to put something on the user interface, they'll call whatever the user interface packages that they're using. If it's Windows stuff and C# or whatever it is they're using, they'll make calls to the appropriate operating system calls or utility calls to do whatever it is that they want to do. Well, in Flames, we never do that. We don't allow our models to ever call underlying host software directly, ever. What we do is we always write a layer, and that layer is in the Flames framework. That's part of what the Flames framework is. So why do we make this layer? The first layer reason is that we can put a lot of functionality in the Flames framework that you would normally have to implement directly in the models. So one of the primary things that we've done over the years is we look at the modeling software and say, how can we make it smaller? It's just across the board, very simple. How can we reduce the number of lines of code? We look at our models, we've got a whole bunch of them, we look at what's happening in there and say, we're doing that same thing over and over on all these different models. Let's figure out a way to push that functionality into the framework so we can take that code out of the models. And as we talked about, the lifecycle cost of software is directly proportional to the number of lines of code. If we can cut down the number of lines of code that have to be written for a software model, we're just automatically reducing the cost it takes to develop and maintain that model. So that's the first thing that the reason we do this is we put tremendous amount of functionality inside of the framework. The other reason we do it is it insulates us from the changes in the underlying operating system. We were working on computers at Ternion for 30 years, and we had a career before that at other companies. So when I was first starting working on computers, we had that big monolithic system. But when desktop systems came out, they were 16-bit computers. So I went through the transition from 16-bit to 32-bit. And that was a big thing. All of our software had to be adjusted because of that. And of course, now we've gone from 32 to 64. Well, I've been there before. I've seen all this happen before. We learned, and that's just a small thing. So many other things about the operating system. Windows has changed. Linux has changed. Unix has gone through different flavors. It doesn't stop. It just keeps changing. Well, if you're making direct calls to those operating system and utility things in your software, and they change something underneath it, you got all this software you got to go back and change all the time. He said, forget that. We're going to write our own API that we can hold constant while we change the framework to adapt to the changes in the underlying operating system. That's huge. That is huge. That's one of the reasons why existing constructive simulations are not real polished, is because they're still using old operating systems and old user interface stuff. And it's just too expensive to go through and rewrite all that code to make use of the update stuff. And you're going to have to do it again next year because something else is going to change. We fixed all that. Our modeling software has remained constant over dramatic changes in the operating system. And I'm going to talk to you about that a little bit more. The other thing is we support Flames on multiple platforms. The operating systems and utilities are different on those platforms. And again, we provide functionality in our framework that far exceeds the functionality that's available in the host operating system. So those are the reasons. And then again, I mentioned this already. As we add new functionality, we've defined an API, and again, we've had lots of years to figure this out. Our interfaces don't change. Or if they change just a tiny little bit. So as we're releasing new functionality in Flames that we're adapting to, we went from 32-bit to 64-bit, we didn't change our models at all. We figured all that stuff out, and the models still work the same. We've made dramatic changes to the architecture and functionality of the Flames framework without having to change the models at all. And that ultimately saves overall cost of the constructor simulation. We're over here updating the product. You get the new release of the product that has all this new functionality in it. you don't change your software at all. Or if you do, it takes you a day and you go through the what's new section and say, you got to add this argument here and do this here and you follow the instructions and you're up and running with the new version. Again, dramatic cost change, savings, dramatic. So here's one example, the Flame scenario database. We don't make any operating system calls to store any of the scenario data. We store all the data in a database management system that we built custom for Flames. It's designed specifically for managing scenario data. It is not as capable as a lot of commercial software databases. However, it has features that no commercial software database supplies. We looked at all the commercial software packages. We can't find anybody that does what we need it to do. And I'm going to explain what that is here in this presentation. So here's some of the features that it has. We wrote the API to our database to allow the data of an entire object, all of its parameters, however many parameters it has, you pass the address of that object into the database and say, save it. It saves it. Just saves it. Now that's not every object. Some objects are more complicated. You have to make a few more calls. But most objects, just pass in the address of the object and say, save it. Our database understands where all the data is and all the objects, and it can just save it for us. So when we implemented this capability in the database, our early versions of Flames didn't have this. When we implemented this, we threw out over 10,000 lines of code in the model. Just threw it away, just deleted it. And that's an example of how when you add more functionality to your framework and you make your models call your framework to do work, the framework can do things for you that typical systems can't do, and it reduces the number of lines of code, which means reducing the cost. Our database supports multiple users with access permissions. Can't do that with normal flat files. Most simulations out there today, if you go look at them, they're all using some kind of flat file. They all have their scenario files. They all have their flat files out there. And there's just issues with doing that. You can't set up permissions. You can't easily share data between multiple scenarios when all the data is all in just one big old scenario file or a set of scenario files. Any part of our scenario data can be shared among multiple scenarios. Again, contributes to making it easier to build simulation, build scenarios. This is the biggest problem. Any application, Microsoft Word, Excel, Visual Studio, you name it, if they save their data on a disk, they've got stuff that's persistent. And it causes this problem. Every software vendor that saves its file disk has to deal with this. Everybody does. That you change your program and you now have different things that you want to save. So that means you have to go through and change the software now to read and write those additional parameters. So that's the first problem that you have. So say you have a sensor model and you want to add an additional parameter to your sensor. You had 7 parameters before and now you have 8. So you got to go change the software of the sensor model to now write out 8 parameters. Both save that data and then read in 8 parameters. So you change the I/O software. The worst problem is now you've got all these old parameter files that all have just 7 parameters in them. But your read code has been written and been changed to be able to read 8. So what do? If you just leave it alone, your read code's going to fail. It's going to go through and try to read 8 parameters out there. There's not 8 parameters there. Your I/O code's going to fail. So what do? And everybody has to deal with this. That's why Microsoft Office files, it used to be .dot. What is it now? .x. Because they changed the format of the Word files. There's a couple of different ways that vendors deal with this. One of them is the way Microsoft does it, Microsoft Office does it. They keep inside of Microsoft Word all of the old read code and all the old write code that they ever had. And every time they add a new format, they have to be able to convert back and forth from that format. And if you go save as, you can save it as a Word 2007 file. That's one of the ways to solve that problem. It's a lot of work to be able to deal with that. The other way to do it is the way Visual Studio does it. Visual Studio doesn't have ways of reading old files. It only works with the current version. But if you open up an older file, they have a converter that gets set off, and it will convert your project files into the new format. But it warns you when you do this, once you update it, you're not going to be able to open these project files anymore in a previous version of Visual Studio. So that's another way to do it. You just write these converters, but you still got to write those, and you got to write those every time you edit, come up with a new version. You got to write a converter to go from all the other old versions that you had to the latest one. And again, this is everywhere, and simulation guys have to deal with this as well. So lots and lots of extra software that you have to deal with. And think about this, if you have a framework like Flames that has all these different components, each of them have their own lives, their own set of parameters, they're all being saved in these files, you just multiply this file problem by hundreds. Because you've got a whole bunch of different people all changing their software, and it's all getting stored into the same data. So here's what we do with Flames. We have made this so that because Flames does all the I/O for an object, the objects don't know how. They just pass in their object into Flames and say, write it. And Flames handles it. When the object gets updated, Flames handles it. Normally, the read-write code does not have to change at all. So you just go into your class, and you change you add a new parameter to your class. And there's a place in the initialization of the class where you tell Flames about the fact that this new parameter exists. And your I/O code doesn't change at all. Doesn't change at all. So we have this whole effort that you have to deal with. We don't have to deal with it at all. More importantly, the database automatically, because it's aware of that new parameter, it automatically adjusts for the presence of that new parameter. And it can read old files in the database and map them to the new class, or go the other way automatically, just automatically. So what that means is our database is forward and backward compatible with whatever version of Flames we have, with no work of the developer at all. None. You guys ever watch Star Trek movies? You watch that? People who've been here before, I tell this joke all the time. There's one where they go back in time to the original Enterprise. And Scotty, they have some trouble with it, and so Scotty's going to come up there, and he's going to try to help him with it. So he gets up to the bridge, and he says, computer. Of course, nothing happens, because they didn't have voice recognition back in the first version of Enterprise. He looks at a keyboard, and he says, oh, how quaint. And then he sits down and types the keyboards in. Now, how he does that, since he's never used a computer before. But we look at file format conversion problems and having to modify code when parameters change, and said, oh, you got to modify the software before parameter changes. How quaint. We don't have to do that. That big effort is just completely eliminated. No debugging, no testing, no nothing. We just don't have to do that at all. So there's an example of how to do that. Well, again, we put this layer in here so that we can add new features to our database without having to change the code. And here's the feature that we're working on. We are now making our database system support collaborative data editing. Flames is getting used in larger and larger exercises. We are now the air simulation for WFX exercises, if you've heard of those things. Flames-based simulation is the air simulation for that entire exercise. Large exercises that we're supporting. There are times now when we have to support multiple people editing scenarios simultaneously. And so what we're doing is we are, if we had all of our data stored in just regular flat files, having two programs edit the flat file at the same time, you can't do that. You ever opened up a Microsoft Excel spreadsheet and it comes up with this little message that says somebody else is editing this spreadsheet right now. You can't edit it. You want to open the read-only copy, or do you want to exit? So you say, okay, I'll read only, and then you can't save it because somebody else was editing that file. Well, that's what would happen with the scenario. You just can't have multiple people do it. When the database, we can, but we can support individual object data locking. So when one application is up editing, there'll be a little lock symbol and says, well, somebody else is editing that object. Not the whole file, not the whole scenario, just the individual object that's being edited at that time. When another user gets off of that, it becomes unlocked and you can change it. And if they make a change to it, it's going to automatically show up in your system in real time. Those are the kind of features. That's what I'm saying. We have features that nobody else can support because we've had a chance to work on this. And it's just amazing what we're going to be able to do with this. Well, another area, and this one's even more significant, in the graphical user interface world, we're talking about a roller coaster ride. These issues of having to insulate ourselves from the underlying host system, those have been huge. And if you think about the number of lines of code that occur in a simulation for saving and reading and writing data to a disk, if you've ever done any graphical user interface program, it is tremendously code intensive. Lots and lots of lines of code are required to put fields and buttons and menus and everything on the screen. Lots and lots of lines of code. We have a system just like the I/O, at Ternion, we like to do things with entire structures, entire classes at a time. We can put all the data in a given object on the screen with one subroutine call, and it has just 2 arguments. Boom, it all shows up on the screen. No user interface code in your model at all. None. Nada. So, not 10,000 lines of code, tens of thousands of lines of code get removed from our models because they don't have to do any user interface programming. So again, just tons of code. However, we allow our developers to each define whatever graphical user interface they want for each model that they build. So you're not restricted on fitting into some crammed interface. You can build any user interface you want for your model. And then whatever user interface you build automatically integrates into our application. So this is kind of what it looks like. And now you're going to learn a little bit more about how you do Flames development. When you want to write a new class for Flames, say it's a new sensor class, pick that as an example. We have a tool, it's called the Model Component Copier. And you can run that tool and you browse to an existing sensor class that's the closest to what you want. And we ship Flames with a bunch of source code to a bunch of different sensor models. Maybe one that you wrote before, maybe one of our, what we call our example models or our bundled models. You browse to that sensor and say, that's the one that's closest to what I want. You run this tool, its little wizard walks you through it. It creates a copy of that class that, when it's done, is fully functional. It works. It's an exact copy, but everything's been renamed now to be what you want your new class to be, and you're ready to go. We don't ever write Flames plugins from scratch. We have a tool that generates the initial code for all of them automatically. So another place where we're super productive. In that process, for somebody who's done it before, it might take 5 minutes. So I've got a whole new class for Flames, totally conform it to all the Flames interfaces in 5 minutes. Then I start going in and changing parameters. So if I want to change parameters for, again, I don't have to modify the code at all, the I/O code, if I want to just completely redo all the parameters for the class. I just redefine them, tell Flames what they are, and boom, it's done. So anyway, I generate the code for the model component copier, and I get a custom source code, and then we use standard development tools. We don't use Visual Studio on the PC. We use other standard tools on Linux, so you don't have to use something different. You use what you're used to using. But when you build that, you create what's called a DLL. And if you're a software developer, you know what that is. And so that's the output that comes from building a Flames model. It just goes into a DLL. Well, you take that DLL, you throw it in a particular folder, or you set an environment variable to tell Flames where you have your DLL, and you restart the Flames application. And boom, your code shows up in the application. It shows up in the scenario editor. It shows up in the scenario visualization tool. It shows up in the scenario execution stuff. You do no integration work at all. At all. Now, this approach to be able to explicitly dynamically load DLLs, we did not invent that at Ternion. Other smart people invented that a long time ago. And a lot of commercial software products use that. Internet, your browsers use that. When you add a plugin to your browser, some extension to it, it's another DLL. That's how they do it. They wrote this interface for what browser extensions need to look like for the browser. Third-party people write browser extensions that conform to those interfaces. When you download it, it puts it in a certain folder, and you go enable it, and boom, it shows up. So we didn't invent this technology. But as far as I know, we're the only ones in the world using it in constructive simulation. We're in the Stone Ages in general in constructive simulation. Everybody's been doing this for a long time. That's what we did. We just looked at other people. We learned from them. We didn't invent this stuff ourselves. We just learned from them, and we apply it here. So integration is just that simple. Throw the DLL in a folder and restart the app, and your code shows up. Now, the most complicated, hands down, the most complicated part of that integration is the graphical user interface. We have a tool that you can use as a developer for every one of your classes, and you can design what you want the user interface of your model to look like. So you have complete flexibility. So here's an example. This is our tool that we use to develop the user interface for one of our simple sensor models. And this is the output from that tool. You get a chance to look at it and see it while you're developing it. You get it and say, yep, that's the way I like it. You compile that, you generate the code from that tool, it gets linked into your model, it gets put in that DLL, you throw that DLL in a folder, the Flames application starts back up again, and your user interface shows up in the sensor editing window inside of Forge. Forge is our scenario editor. So that interface shows up in our window. And any interface that any model has shows up in the window. So every interface is custom to that model. In terms of plugins and interfaces and being able to take stuff into a framework and be able to integrate it automatically, that was hands down the hardest thing that we had to solve. Extremely difficult. And it's, to our knowledge, no one else in the world has solved this problem. We looked at all the other commercial products, all the other constructive sims. Nobody knows how to take an interface and define it in a DLL in a constructive simulation. Now, other people in the world know how to do this, but we've never seen another constructive simulation that can do what you just saw happen there. You let developers build any user interface they want, throw it in the DLL, and boom, it shows up in our application. That we have no idea what people are going to put in their user interface. But whatever you put, we're going to have it show up in our application. So, a little bit of history about this user interface environment. We have written and rewritten this thing many times because there's probably no place, I don't know if that's quite true, but there's few places in the computer world that we live in that get changed more often than the way we do graphical user interfaces. It's just constantly changing. The first version of computers that we worked on was a Silicon Graphics computer. You might remember that. If you've been coming to ITSEC, you might remember years ago, every computer on the show floor was a Silicon Graphics. Everybody did their simulations and SGIs. Unfortunately, they're gone, and now it's a lot of other vendors that are out there, mostly PCs. But back in the day, when we first started working on SGIs, they didn't have a windowing system. Whenever you ran the app, it was command line. This big CRT came up. You got one command line on there. You typed the name of your program, and that program took over the whole graphics head. And then it did all of its fancy 3D graphics. But when it exited, you got back to command line. You did something else. It was single application running at a time. So we wanted a windowing system then. They didn't have it. We wrote the entire windowing system for the first version of our software using rectangle and line drawing routines. It was gut-wrenching to build a custom windowing system completely from scratch. But that was the first version that we did because we wanted our applications to have an interface that looked like the Macintosh because that was the newest thing on the block at the time. Well, finally when SGI came out with a windowing system. And it was called MEX, and it was really crummy. We didn't even bother supporting that. The next one that came out, that was based on PostScript. Believe it or not, they had a PostScript user interface. It was called News. So we implemented that. We rewrote our stuff to make. Finally, they got a host windowing system. It's not going to be as much work for us. Our modeling software didn't change. Didn't change a line of code in our modeling software. We rewrote the user interface, and now it was this thing. And over the years, it's just changed more and more. Now they're all, Linux world is all X Windows, and that's been pretty stable. The Windows world is still not so stable. They've gone through all kinds of different things. Plus, we've been ported to different platforms, and they have different windowing systems. We used to run on a Macintosh back in the day for a little while, and then we decided not to do that anymore. Moved to the PC, we went to Sun, went to HP Linux machines. We're pretty much now working on just Linux, variations of Linux and PCs, but Windows keeps changing things, and the world keeps changing. Through all those changes, all those different versions of Joule, massive rewrites there, our modeling software has remained the same. So we get to do all this stuff, keep up with the latest technologies and user interface, and the software that we wrote for models, we don't have to change that. You realize how much money that saves? I mean, millions and millions and millions of dollars get saved by not having to do that. But most people don't spend those millions because they don't have the millions to update. So their user interfaces still stink. They're still based on old stuff, but they may not even have one because it's just too expensive to write graphical user interface. And you don't get the quality because you can't afford it. With Flames, it just comes off the shelf. Now, here's a really big thing that we're doing. We all know that there's this new thing called software as a service. And part of that is SaaS. That's the big move in the industry. All the software that you buy, that you use in your desktop, you've seen this happen. Software is now part of one of the ways you get SaaS is you run stuff in the cloud. So, Microsoft Office, you can run Office apps in the cloud. QuickBooks, there's the cloud version. You just go down the line, the whole industry is moving toward having software based on a server. And basically, you're running the application in a web browser. So you don't have to install software on your computer anymore. You don't have to worry about keeping it up to date and downloading the latest updates. The server stays up to date. You just open a web browser. As long as you've got the right web browser installed on your computer, you can run the software. The whole industry has moved that way. It's been moving that way for a while, and practically everybody now has in the cloud-based versions of things. Our customers are saying they would like to be able to run simulations in the cloud, which means being able to run our simulation software in a web browser. Well, if you look at how people write, the web is a completely different animal. It's just, not anybody's ever done web programming, really trying to not write a web page, a static web page for your company or something like that, but write a piece of software that runs in a web browser. It's tough. And it's very, very, very different, because everything is HTML and JavaScript that you're sending back and forth pretty much, regardless of how you get there, whether it's ASP or whatever, you're ultimately sending HTML. And it's just a completely different animal. And we have been scratching our heads for a long time saying, okay, we've got this world that we live in where our models have this API, and they're all written in C and C++. And if you're going to use, say, Visual Studio, ASP.NET, where you got to be working on .NET Core, you got to be working in C#. So we're going to rewrite all our code in C#. And how do we do all this? I've researched everywhere. Who can do this? Who can take normal C code and run it? Nobody can do it. We haven't found anybody that does it. So we worked on it, got smart folks at Ternion working on it. This is what we have now. We have written software, a new version of the Flames GUI services, that will allow us to run applications, C and C++ applications, in the cloud, in a web browser. And we're able to do it just by rewriting the GUI services. And what we expect is that, as before, our modeling software is going to stay the same. Same modeling software, same DLLs, same exact DLLs. We're going to load them in a different application, and those applications are going to run in a web browser. Now, we don't know yet if we're going to be able to make this happen. We are doing this already now. We've gone far enough to say, and I got enough to say, I'm at least going to talk about it. We can run some of our internal applications now that we've written using the Flames GUI services. We can now run those in web browsers. We're super excited about it, and I'm so excited. Thank you for taking the time to let me tell you about it. And with that, I've come to the end of the presentation. So, thank you so much for taking the time to be with us, and we hope you have a great day.